Welcome back to our course in probability theory. Today we are starting the last part or the last section of the manuscript and of the full course, which is conditional expectation. In the basic course of probability theory, you already learned what conditional probabilities is, and conditional expectation is a bit more general. And above all, the definition of the conditional expectation will be very different from what you heard in the basic probability course, because we now have measure theory at our hands. So let's get started. So, conditional expectation. Let's start what you already know. You know a formula which looked something like this. That's a conditional probability. So the probability of some event A given some event G is, by definition, the probability of the intersection divided by the probability of the condition. A bit more general is conditional expectation, and you can define it also in a very similar sense, like this here. So expectation of some random variable x given some set G. That's the expectation of x. So on G, so just let me remind you that that's the same as the expectation of x times the indicator of G. That's the numerator here. Divided, as in the conditional probability, by the probability of the condition. Okay, of course, this only works if the denominator here is not 0. Otherwise, you will have a hard time defining this properly. And we would like to have this here in our course not only for events here, but for sets of events, so for set systems. And for this reason, we want to define something like this here. So what should this mean? So G here is a set system which is smaller than the sigma algebra that we are given. And smaller means we only have fewer sets at our hands in G. And that means we have fewer information about the randomness that happened in our experiment. So, and for this reason, G contains less information, but we can get some expectation given we have this fewer set of information G. So that's how you should think about this. And let me start with a basic example with a specific G here. For this, take some sequence of sets which is a partition of omega, which means the intersection of Gi and Gj is the empty set and the union is the whole space. And let's also assume, well, for simplicity, I think I'm going to need this, that the probability of all these Gi's here is positive. And the sigma algebra I'm considering here is the sigma algebra which is generated by this partition. So what should this here be? So what should the conditional expectation given G be? First of all, this is a random variable. So I can plug in some omega here. And what is it? Well, first of all, it should be this here by definition. So if I'm on the set Gi, then this should be here the conditional expectation of x given Gi by definition. And I'm summing over all I here, which means I will get a random variable here, where this here is the kind of randomness, saying on which set of the Gi's I'm in. That's the definition. And then let me prove something for this, which will then be important in the later course of this video and also the next. Let's say we have some subset of the natural numbers, and A is the union of Gj over all these sets in J. Then I can make the expectation of the conditional expectation along the set A here. So A here, you should think of A as G measurable, right? So A is G measurable because, it's a finite or countable union of sets in Gj, and Gj generates G. That means A is a generic G measurable set. And the expectation of this conditional expectation, which is given like this here, okay, I can plug in the definition, expectation of the sum here. Sum and expectation, okay, they interchange, so like this. And now, what else happened here? Something else happened. Indicator of Gi times indicator of A. A is a union of these Gj's. So what happens is, well, if I is not in J, then here's a 0. But if I is in J, then I can forget about the indicator of A. So I have this here. Yes, so like this here. And the expectation of X given Gj, well, that's the expectation of X given G. So like this here. So that's a real number. I can plug that out of the expectation. I have the expectation of the indicator, which is the probability of Gj. And in the denominator, I have the same thing, which means I end up with this here. And then I can again sum over all the j's, and I get the expectation of X over A. Okay. And you must recall this now. So we have proved that the expectation of X over some set, which is G measurable, is the same as the expectation of the conditional expectation given the same G measurable set. And we will use this later. But let me first make one more example, which is also an example which I like very much, and that's the following two-step procedure. U is uniformly distributed over 0, 1. And given U, well, U can be any number between 0 and 1, uniformly distributed. I roll a coin and n times, and I get the number of times with a success, with a random success probability U, and that's my X then. And, well, for example, the probability that X equals K given U is apparently this here. K choose N, U to the power of K, 1 minus U to the power N minus K. So you should read this here as conditional, I know what U is. Conditional on, I know what the success probability is. And then that's here just the binomial distribution formula. Using this, I can, for example, compute the expectation of X given, for example, U is less than a half. For example, like this. And okay, this here has positive probability. I should be able to compute this by hand, by the definition that we had. So that means by this formula here. The probability of the condition, well, the probability that U is more than a half, that's a half. Divided by a half means I can also multiply by 2, so I have this here. And in the numerator, I have the expectation of X times something. Well, and how can I compute this? First, I have to see what U can be. So it can be any number between 0 and a half with equal probability du. And given this, X is binomial distributed like this here. and I have this kind of expectation formula. Of course, we know what this is here, because this is just the expectation of a binomial distribution, which is n times u. That's written here. And I have 1/4 times n. Okay, that was one example for such a conditional expectation. On the other hand, you can also read off here the conditional expectation of x given u. Okay, given u, we know that x has a binomial distribution. And for this reason, because it would be n times p if x would be b and p distributed, but now it's x and u distributed. And we already said that the conditional expectation here is a random variable, so that's also going to be a random variable, which is n times u. So that's an example. But let me start here with one main result, which is the most important result of this video. As above, G is a subset of F, G sigma algebra. And I want to define a map which sends here, what's not written here, a random variable to another random variable, which is then the conditional expectation of x given G, such that this conditional expectation is a G-measurable, integrable function. And the property that we require from this function is as before, as in this calculation here. So the expectation of the conditional expectation on some G-measurable set equals the expectation of the original random variable x on the same set A. And it's stated here, there exists an almost surely unique such thing. Okay, so that's the claim. So there exists almost surely unique such thing. I'm going to show you this only in the case where x is 2 times integral x and L squared, because then we know that the L2 here, is a Hilbert space where we have a scalar product, and I can use that as follows. I can say I have a linear subspace, which is the set of y's, which are in L2 and, well, G measurable. And that's a linear subspace, because if y and y prime are in M, then y plus y prime is also G measurable. And for this reason, because we're in a Hilbert space, there is a unique element y in M and z perpendicular to M with x equals y plus z. So that's a standard thing. So y is the projection of x to this linear space. I can do that with any linear space, and I can decompose x into y plus z by standard theory on L2 spaces. And then I can define set the conditional expectation of x given G equals y. When I do this, I already know y is in M, which means the conditional expectation here is G measurable. That's the one thing. On the other hand, I know that z, which is x minus y, is perpendicular to M. So x minus the conditional expectation is perpendicular to M, which means the scalar product of this here, x minus the conditional expectation of x given G, on any set A, which is G measurable, must be 0. Yeah. And that's already it. I also have to say that y and z are unique by standard theory in Hilbert spaces. And using this, I can say that, okay, expectation of x given g is almost truly unique. So by now we have defined the conditional expectation by this defining property. I will call this here the defining property of a conditional expectation. But that's not the end of the story, because I can prove many things about this. First of all, well, the one here I have already. The second property will be if x is non-negative, then the conditional expectation is also not negative. I have bounds, something like the expectation of the absolute value of the conditional expectation is bounded from above by the expectation of the absolute value of x. And there are versions for monotone convergence. If xn grows to x, then also the conditional expectation grows to the conditional expectation of x given g in L1. Let's start to prove this and we start with property 3. First of all, let me say A, that's a set. That's the set of all omega where the expectation of x given g is bigger or equal to 0. And since the conditional expectation here is g measurable, the whole thing here is in g. This here is in g. And for this reason, I can start on the left-hand side, the expectation of the absolute value of the expectation of x given g. I can write it like this. I can split the outer expectation using an expectation on the set A. Okay, on the set A, this thing here is positive, so the absolute value equals the thing itself. And on A complement, it equals minus the same thing, so the minus the expectation of conditional expectation on the complement of A. Then I can write further by the defining property of the conditional expectation, since A is G measurable. This here is then expectation of X on A minus the expectation, or let's say plus the expectation of minus X on A complement. Both X and minus X are small or equal to the absolute value of X. And I can collect A and A complement. So I have this bound here, and that's what was claimed in the third property. Okay, let's continue with the second property. So A is not negative. And similar to above, but just the other way around, I can say I need yet another set A which is G measurable. That's the set of all omega where the expectation of x given j is smaller or equal to 0, which is a set in G. Then when I have this, I have on the one hand that the expectation of the conditional expectation of x given g over the set A is not positive because the random variable which I'm integrating on the set A is not negative. On the other hand, this here is the same by the defining property of the conditional expectation of x given A. But since x is not negative, that's also not negative. And I have this system of inequalities, which means everything is 0 here. Which means, so what should I conclude here? Well, that means that A is a set of size 0. Then let's continue. Fourth property. Monotone convergence. We have xn grows to x, and then we need to see that the conditional expectation also grows to the conditional expectation. First, we have that xn minus x goes in L1 to 0. And therefore, we can write the following. The expectation of the absolute value of the conditional expectation of xn given g minus the expectation of x given g. I have to show that this here also goes down to 0, because that means nothing but the convergence of the conditional expectation of xn given g to the expectation of x given g in L1. So what can I do? Expectation is still linear. Expectation of absolute value of conditional expectation of xn minus x given g. Then we know from property 3 that this here is bounded from above by the expectation of absolute value xn minus x, and that converges to 0, as we just saw here. Okay, but that's not the end of the story, because there are more properties we can show. So we have a 5th, 6th, 7th, and 8th property. First, if x is g measurable, then there is some calculation going on here. So this x here is g measurable, and I could put it out of the expectation. Since it's g measurable and the expectation of y given g is also g measurable, I know that the product is also g measurable, which is a good sign. But I will start with this property 6 here, where 3 things here are the same, which are kind of symmetric. I have x times the conditional expectation of y given g, and I can exchange x and y here inside the expectation, and I can also write the conditional expectation instead of x itself. Let's see if we can prove this. Again, I'm only doing this if x and y are in L2, because then I have this linear space M of g measurable functions, and expectation of y I need here. Y given g is in M. And for this reason, the scalar product of this thing here, expectation of y given g, and any member which is perpendicular to M equals 0, and the thing is which is perpendicular to M is x minus the conditional expectation of x given g. This here is 0 by general theory. And this already shows everything, because I have here x times the conditional expectation. I can pull this apart here, this minus here. So I have proof that this here equals this here. And by symmetry, I can then also show that this middle term equals the expectation of the product of the conditional expectations. Okay, that's this. And then we have property number 5. So property number 5, x is g measurable. And then I can pull out the x here. Take a in g and take the expectation of x given g times the indicator function of a. And since x is g measurable and the conditional expectation is unique, this here is almost surely the same as x times the indicator of I. And for this reason, the expectation of x times y on the set A is the same as the expectation of so here I have x times indicator of I, the expectation of the conditional expectation of x given g times y on A. And this here, well, we just learned this. I can exchange x and y here. That's the same as the conditional expectation of that's the same as the conditional expectation of x times the conditional expectation of y given g on the set A. And what do I want to prove? Yeah. And that means the conditional expectation of x times y given g, that's by definition the same as the only g measurable random variable which expectation like this here. And what I have here, x given g times y, which is the same as the expectation of x times the expectation of y given g on the set A. And this here is also g measurable and has the defining property. So this here it must equal the conditional expectation. Okay, that was this. And then we have two more properties, 7 and 8. 7 is something which we will need often. I have two things here. I have g and h. H is a subset of g, and I condition on g first and then h. And the result is I can also condition only on h. Okay, this here again is h measurable, and that's also h measurable. Let's take some a in h, which is also in g, of course. And then I have to see if the defining property holds. So the expectation of the conditional expectation of x given g on the set A. And what I have to see is that this here equals the same, but with the h here, because then I have found an h measurable random with a defining property. This here is by definition the same, since A is also in G, as the expectation of x on the set A, which is by the defining property of the conditional expectation of x given h, the expectation of the conditional expectation of x given h on A. And so we have shown what we had to show, which is exactly this. That's also called the tower property, because there's h subset of g, which is a tower, and you only need to take into account the base thing of the tower, the smallest thing, the h. The last property, number 8, if x is independent of g, then you can forget about the condition, and that's just the real number expectation of x. So if a is in g, and x is independent of g, recall this, then I have that the expectation of the conditional expectation of x given g on the set A is the same as the expectation of x times indicator of A, which is by independence the same as the expectation of x times the expectation of the indicator. And I could write this in a quite funny way. The expectation of, well, I pull in to this expectation the real number expectation of x, and then I integrate over a. I can write it like this. And this here, of course, is a g-measurable function, which satisfies the defining property. So this here must be the conditional expectation. Okay, so we are almost done. There are some things for the expectation which also then hold for the conditional expectation. There is one result which I'm not going to prove because the proof is the same as before, which is Jensen's inequality. You know Jensen's inequality for some phi convex and the usual expectation operator, where the expectation for convex function is bigger or equal than the function of the expectation. And that here also holds when you condition on some sigma algebra. Okay. And the proof, as I said, is just the same. There are two more things I would like to say. First, there's one thing which is, I think, very nice because it connects several things. Assume you have an integrable random variable x, and you consider all possible conditional expectations. Then, as we'll just see, that's uniformly integrable. So this huge set here is uniformly integrable. Why is that the case? I mean, there was something that we proved already. Uniform integrability. First of all, the set X is uniformly integrable because any finite set of integrable random variables is uniformly integrables. And we have shown that there exists a phi from R plus to R plus, which is increasing and convex. And phi of x divided by x goes to infinity. And the expectation of phi of absolute value of x is smaller than infinity. We have also shown that if there exists some function like this here, is the same as, well, we have a supremum here, that's the same as uniform integrability of the family. And now we have this, and I can use one property in order to show that the supremum over all f subset of A, or let me not say f here, but maybe g is a better letter, because it's the same as the g here for the index of the family, of the expectation of phi of absolute value of conditional expectation of x given g, like this. But now I have here phi of a conditional expectation, and phi is convex and phi composed with the absolute value is also convex. And we just proved that phi of this here is smaller or equal than the phi on the other side. So it's smaller or equal. Sup stays, but will be gone soon. Expectation of conditional expectation of phi of absolute value of x given g, like this here. And now, I have an expectation of a conditional expectation. But the outer expectation I can also write as a conditional expectation with respect to a very trivial sigma algebra, which only consists of 0 and the whole set. That's something you will have to think about probably, or maybe put that into the exercises. But that's true. And then we have the tower property, because now we have an expectation of the conditional expectation, which is the same as the expectation of phi of absolute value of x, and that's finite. So we have this thus proved. that the supreme here is finite, and that's the same as saying that the family, which is written down here, is uniformly integrable. Okay, last thing. Dominated and monotone convergence also holds for conditional expectations. So we know that if xn grows to x in L1 almost surely, or if you have a dominated function y and xn goes to x almost surely, then the expectation of the xn converges almost surely in L1 to expectation of x given g. And again, the same here holds true if we have not the expectation but the conditional expectation. And the proof is, well, almost the same. You need to use the defining property, and you always also have to use that the expectation of conditional expectation of xn given g minus expectation of x given g is smaller or equal than the expectation of xn minus x, which by assumption converge to 0, and therefore you also have it for the conditional expectation. Okay, that's it for today, and next time we're continuing with the conditional expectation. See you then.